Alright, hey guys, what's going on? So today we're going to be talking about interacting quantum fields. Interacting quantum fields is the first stepping stone to getting into the really interesting stuff regarding Feynman diagrams, renormalization, stuff like that. So let's get right into the material, but before we do that, make sure to hit that like and subscribe button. Now let's get into the material. So today we're talking about interacting quantum fields. This is going to be a short video. I just want to prime us before we dive deep into some of the more mathematically rigorous stuff, which I will try to make fun and interesting for you to follow. That's the whole point of this series, which is to take the more mathematically rigorous or more scientifically rigorous concepts and present them in a way that's hopefully understandable. Anyway, the first thing we want to do when we're considering interacting quantum fields is to say, we have some arbitrary state, right? Some particles might be in some state. They start in that state, okay? And then they're going to end in some different state. That's all we're saying right now. We're not really defining anything about the states. We're just saying there's a beginning state and there's an end state. We're not going to stipulate what describes these states yet. We're just going to say we're going to have an initial state or a configuration of particles. And we're also going to have a final configuration of particles. And these are going to be described by these two ket vectors. Now, if you don't remember from quantum mechanics, ket vector, right, looks like something. There's something in here, right? This is what the vector looks like. It looks like a greater than sign, right, with some stuff in there, with some stuff in here, and then this line, and then there we have this what's called a bra vector. The bra vector is going to be the complex conjugate of that vector if they're the same, right? If they're different, then they're obviously going to be different. But this is the bra vector. Together, they make a bracket, bra and ket, right? This was Dirac's notation early on. We just want to remind ourselves of a little bit of quantum mechanics before we dive into some more details here. Anyways, we start off with an initial configuration and a final configuration. Okay, and now what can we do with these, right? Well, this initial configuration can be a superposition of basis states, suppose, right? So if we think of this as a vector in some 3D space or 4D space or 5D space, right? The vector in 3D space has, the way you describe that vector is through weighted sums of the basis vectors, right? And that's exactly what we're doing here. These are some arbitrary basis vectors, and the C's are the weights on those basis vectors that make up the initial state, okay? So you might think we're just making more brackets, or we're just making more ket vectors. What's the point of all this? Well, bear with me. So if we bracket our final state with, and I don't need to, actually what I want to do here to make this a little bit easier, I'm going to put an F right here, and I'm just going to make this an F right here. Okay. And if we have, I'm going to label that 1. Okay, so if we have some final state, one final state, say, what we want to do, right, is we're going to bracket that with all of these terms, right? So here's the same, this state, same state here. We're just appending it onto these guys right here, okay? Now the point here is that we want to, what do I have going on here? This should be, those are the basis states, right? So this notation is a little bit weird that I'm using, but these are the basis states. These are the final states, right? So basis states, final states, and essentially, it's because these two numbers here are different, this 1 and this 2. This thing is going to cancel out, right? Because we're supposing that they're orthogonal to one another, okay? That means this here, this is going to be F1, F2, C2 like that. Well, if they're orthogonal, this is going to be 0. Right? So the only thing that we're going to get out of this is this weight, the weight here. So when we attach our final state, this final state specified by this one, there might be multiple final states that we want to consider. Well, if we specify only this one, we're going to get the weight that's associated with the first basis state. Okay? So that's how we can calculate these guys. If we know these two, right? If we know this and this, we could calculate this. Right? So far, so good. This isn't too complicated, hopefully. So now I want to shift our focus a little bit into talking about this operator, this time evolution operator that we've talked about in the past, right? So this time evolution operator is this thing that is this operator that operates on these states, and these states are they obey the Schrödinger equation, but the operator itself, as time evolves, has to also obey the Schrödinger equation. And so what we found out is that if we want the time operator, or this time evolution operator, to obey the Schrödinger equation in its dynamics, then it must take the form that looks like this. Right? This is a Hamiltonian. This is an integral over this parameter that defines the Hamiltonian, and in this case it's time, and we're exponentiating it to get this time evolution operator. Now there's two things that this time evolution operator can do, and we want to capture the essence of both of these things. One of them is to rotate the initial to the final state. Okay, right? So we have our initial state and initial state, and I realize right now that my notation here is a little bit weird, right? Because I'm saying initial state here, final state here, which is why I had this be an I initially, because it's I of t, not I of 0, right? You can replace, here's I of t, so I of t, again, I of t here, this looks like a final state, right? The idea here is that you can take a state, right, break it up into its multiple basis states, and then filter out which basis state you're interested in by appending this right here to a final state that's associated, say, with the first basis state. Right? This is all really just a little bit of mathematics, not super important for right now. Anyways, there's two things that we can do to consider the evolution of some state, right? One is to actually rotate the state like we're doing here. This is called the Schrödinger picture. I like to think of these dynamics in these pictures because I'm very much a pictorial thinker. We can actually rotate the state like we're doing here, or we can rotate the basis vectors, and that's what we mean when we go up here and we say these are the basis vectors, and these things can change also, right? And this down here this is the Heisenberg picture, right? So the Schrödinger picture says we have a state, we use some time evolution operator to evolve it into a final state. The Heisenberg picture here, the Schrödinger picture here talks about using evolving the initial state to the final state using this operator. The Heisenberg picture here says, okay, we have this state, this initial state, we're evolving into a final state. But what we want to do is we're first going to evolve the let me reword that. We want this state, these two states here are going to focus on evolving the this the initial state. Same thing here. This is going to do the same thing to this state. So essentially, U dagger, that's going to be 1. So we're not really doing anything to change the state here. We can see it's pointing in the same direction, right? What is actually going on is that this guy right here is going to be doing the rotating of the basis states, okay? So that's the Schrödinger picture and the Heisenberg picture. And what we now want to do is we want to mix the Schrödinger picture and the Heisenberg picture to consider the time evolution of both states, and we want to capture the essence of both of them. The way we're going to do that is we're going to take this Hamiltonian here, so this Hamiltonian with a subscript f, is going to describe a system of all interactions, if all interactions are ignored, whereas this u of f is going to do it on operators if all interactions are ignored. Okay. The I, so F stands for free, right? So we're ignoring interactions. Here, when we have I's, we have interaction terms, right? So what we're capturing essentially 3 things here. One is the time evolution of the state. The other is the time evolution of the basis, and the other is interactions and a free Hamiltonian and a Hamiltonian that has interactions within it. Okay, so it's 3 things. Right. Interactions or not, evolution of basis and evolution of the state itself. Okay, so the way we capture that again is this is the evolution of the states, the actual state vectors right here. Right, we are these theoretically should cancel out because we have not. Cancel out, but this and this equal 1, this and this should equal 1, and then we have this operator acting on the basis, right? So we're in some sense, this object here is capturing the dynamics of everything that we want to talk about. We are considering interactions, right? I want to use my pointer. We're considering interactions, we're considering the free form, and we're considering the evolution of the basis. Okay? Now we want to define now. You might think, okay, I am defining so many things. This seems to be an unstructured topic, which is kind of true. It is a little bit unstructured, but I'll feel much more comfortable talking about later things once I get this out of the way. And so we're defining this term here now without subscripts to contain the free and the interaction portion. We're going to do the same, but we're going to see there's the same thing with the Hamiltonian. And the way we see the same thing, if we stipulate this definition, right, the operator must evolve according to the Schrödinger equation, right? So that means this has to take this form. Well, this form we're going to define now as just being, we're multiplying again, multiplication. These 2 things are being multiplied, just as we're multiplying these 2 things. But we'll see that, now we see that we have these exponentials, right? When we have anything to the exponential, that means this is going to be e to this plus this, right? So I can add, I'll add a step here. This is the same thing as e 0 to t dt prime of t plus h I of t. This is all to say that h, actually, do this, e to the minus I h bar dt prime h t prime. This is all to say that therefore this follows, right? Because everything in the exponential has to add, like this. That's where we get this. So when we say that if we stipulate this, right, because this has to obey the Schrödinger equation, so these things have to be multiplied, and if they're multiplied, that means our Hamiltonians must be additive, right? So if the time evolution operator looks like this, then the Hamiltonian for the associated time evolution operator looks like this. And that's really what we want to talk about in this chapter, right? We're beginning, this is chapter 9. This is a relatively short chapter, I think. The next one is going to be talking more, we're going to start looking more at scattering. And that's where things get really interesting and fun. So if you like this kind of content, make sure to hit that like and subscribe button, and I'll see you guys in the next video. Bye.